this video, we will add a syntax highlighter to Microsoft Visual Studio, familiarize ourselves with some of the general purpose registers, learn about a few basic data transfer and arithmetic instructions, and we will write a temperature conversion program to convert from Fahrenheit to centigrade. The syntax highlighter makes it easier to read your programs by color-coding different components in your program. Here is our first program we created in the previous video. When we add a syntax highlighter to the program, aside from becoming more colorful, it is easier to recognize the different components of our program. The items in pink are directives. Directives are commands that are recognized and acted upon by the assembler. They are not part of the Intel instruction set, but instead declare the memory model, the data stack and code segments or areas, and declare procedures. They are not case sensitive, but for clarity, my examples will have these capitalized. The red items are labels. They act as place markers and give recognizable names to aspects of our program. In this program, the one label is the name of our main procedure. Two other common labels are data and code labels, used to name data values and make it easier to move around within our programs. Data labels will be shown in black. The items in blue are instruction mnemonics, and they are the instructions that will be converted into machine code by the Microsoft macro assembler when we build our programs. They are made up of the Intel instruction set. Operands are shown in dark red. Depending on the instruction or mnemonic, there may be anywhere between 0 and 3 operands. Operands can be constant immediate values, such as 5, constant expressions, such as 2 plus 4, registers, such as AX or BX, and memory data labels, such as counter. You will notice the 5 and 3 following the move and add instructions are orange. Memory or data labels will be in black. Finally, comments are in green. Comments are always good. They explain the purpose of a program, a procedure, or a block of code. They are especially useful if you have created a complex set of instructions to explain the process after you've stepped away from the code for an extended period of time, or if someone else must make future modifications to your program. Single-line comments begin with a semicolon. Now we will start Visual Studio and install the syntax highlighter. Once Visual Studio starts, you should see the first two projects we created on the left side of the Get Started page. Select the project you used to add the two numbers from the last video. When the project is loaded, you should see your program in the large window. If you do not see the program, look under Source Files in the Solution Explorer on the right side of your screen. To install the syntax highlighter, we will install an extension to Visual Studio. Click on Extensions at the top of the screen, then Manage Extensions. In the search bar at the top right, type ASMDude, then press Enter. An extension named ASMDude should be displayed in the center panel. Click Download, and when it finishes downloading, note the alert message at the bottom of the window. Your changes will be scheduled. The modifications will begin when all Microsoft Visual Studio windows are closed. To complete the installation, click Close, then click File, Exit. The VSIX installer will begin. Click Modify, then wait for the installation to complete. Now click Close, then restart Visual Studio and reload your program to add two numbers to see the syntax highlighting. Before we move on to writing our programs, it is necessary to understand some of the internal operation of the x86 processor. Modern x86 processors have 8 32-bit general-purpose registers. Each of these registers consists of 32 bits, and each bit can be either a 0 or a 1, representing the number 0 or 1, or a state, 0 for false, and 1 for true. A 32-bit binary value is also referred to as a D-word data type. This will be explained in more detail in a future lecture. A 16-bit value is a word data type. Typically, the bits are split into groups of 8 bits. An 8-bit data type is called a byte. Finally, bytes are further broken down into groups of 4 bits called the nibble data type. To streamline our ability to convey these values to each other, since reading, writing, or speaking long strings of ones and zeros can be error-prone, we express these 4-bit values in hexadecimal form. 4 binary bits can represent a total of 16 unique values. Similar to the base 10 number system we're all familiar with, in order to express all 16 values available in 4 bits, we have to add 6 more digits, A through F, to our number system. Here is a quick overview of the hexadecimal number system. When all 4 bits are 0, as expected, the hexadecimal, or hex for short, representation is 0. The 4 individual bits within the nibble have the values beginning from the right of 1, 2, 4, and 8. Therefore, if only the rightmost bit is set to 1, the hex value is 1. If the second rightmost bit alone is set to 1, the hex value is 2. The second leftmost bit would be 4, and finally the leftmost bit has a hex value of 8. When bits are combined, as in this example, we add the 2-bit values together. 4 plus 1 equals 5. The process gets a little trickier when the bit values add up to more than 9, the highest amount that can be represented in a single digit. Here we see that 8 plus 4 is equal to 12, and we use the letter C as the digit to represent the bit value in hex. Finally, if all bits in the nibble are set to 1, we have 8 plus 4 plus 2 plus 1 equals 15 in base 10, and this is represented using the letter F in hex. In the x86 assembler, numbers can be represented in 4 different number bases: binary, decimal, hexadecimal, and octal. For today, we will concentrate on the first 3. In binary, there are only 2 digits, 0 and 1. To avoid the confusion of the first number 1101 being 1101, we represent it with the trailing B to indicate binary, and it is spoken as 1101, not 1101. In decimal, we use the digits 0 through 9, and this is the number base we are most familiar with, so either no trailing letter is used, or for clarity, the letter D may be used. Finally, in hexadecimal, the digits 0 through F are used, and the letters A through F may be expressed as either upper or lowercase. One important note here: if the first digit of your hex number is a letter, A through F, you must precede it with a 0, or the assembler will throw an error. The 0 forces the processor to think of it as a number. The values in the right columns, 1101 binary, 13 decimal, and 0D hex, all represent the same identical value in our programs. Likewise, 1001, 0101 binary, 149 decimal, and 95 hex are all identical. Now we have a quick overview of the binary and hexadecimal number systems and number representations in the x86 assembler. We will familiarize ourselves with the general registers. There are 8 general-purpose 32-bit registers in the x86 processor: EAX, EBX, ECX, EDX, ESI, EDI, ESP, also known as the stack pointer, and EBP, also known as the base pointer. In order to maintain backward compatibility to programs written earlier, each of these registers can also be addressed as 16-bit registers, by using the low order or rightmost 16 bits. In this case, they are referred to as AX, BX, CX, DX, SI, DI, SP, and BP. These are the registers we will use for the rest of this course. Then finally, each of the AX, BX, CX, and DX registers can also be referenced as pairs of 8-bit registers, with the two halves of AX being accessible as AH and AL, BX as BH and BL, and so on. Today we will focus on 4 of the 8 general purpose registers, EAX, EBX, ECX, and EDX, and for the majority of this course it will just be on the 16-bit part of these registers, AX, BX, CX, and DX, and their 8-bit components. These 4 registers are the 4 registers our template program sets to 0 at the beginning of each of our programs with the XOR, or exclusive OR instruction. This is the register view from the previous video after we moved 5 into AX and then added 3, resulting in 8. Now we are ready to discover some more details about a basic data transfer instruction and some arithmetic instructions. The x86 assembler language has 4 basic data transfer instructions, but for today we will concentrate on just one, the move instruction. The move instruction, spelled MOV, takes 2 operands, a destination and a source. The destination is listed first, followed by a comma, and then the source. With the move instruction, the source can be a register, external memory, a variable, or a constant, while the destination can only be a register or external memory. You cannot move a value from one external memory location directly to another external memory location. In other words, the source and destination cannot both be memory locations. Here are some examples of the move instruction. Move the constant value 5 into AX. Move the value stored in AX into BX. Move the value at memory location referenced by count, defined in the data section of the program, into CX. Move the value in CX to a memory location referenced by count. And move the constant value 12 into the memory location referenced by myvar. In this final section, we will become familiar with 4 basic arithmetic instructions, and we will use them in our first program. The first 2 arithmetic instructions are add and subtract, spelled ADD and SUB, and like the move instruction, each takes 2 operands. Just as with the move instruction, the source can be a register, external memory, a variable, or a constant, while the destination can only be a register or external memory. You cannot add a value from one external memory location directly to another external memory location, just like in the move instruction. Here are some examples of the add and subtract instructions. Add the constant 5 to the value in AX and store the result in AX. Subtract the value in AX from BX and store the result in BX. Add the value at the memory location referenced by count to the value in CX and store the result in CX. Subtract the value in CX from the value in the memory location referenced by count and store the result in the memory location. And add 12 to the value in the memory location referenced by myvar and store the answer back in that memory location. You may be thinking AX is a 16-bit register, therefore the smallest value able to be stored is 0 and the largest value able to be stored is equal to 65,535. What happens if you try to add 2 numbers where the sum is greater than 65,535, or if you subtract a larger number from a smaller number resulting in a negative result? We will leave these two questions for your investigation when you're working on the lab assignment. The last two instructions we will learn are multiply and divide, spelled MUL and DIV. These instructions take only one operand, the source, and it can be a little tricky to understand. The second operand, the destination, is implied and therefore is not explicitly specified in your program. The destination of the multiply and divide instructions is always the AX register and sometimes the DX register. We will go through a few examples of the multiplication instruction to become familiar with its operation. First, move the value 5 into the 8-bit AL register. Remember, this is the lower half of the AX register. Then move the value 10 into the 8-bit BL register. Notice the value in BL is 0A, which is 10 in hex. Finally, execute the multiply instruction using the value in the BL register. To arrive at our final answer, we take the value 5 in AL and multiply it by 10, the value in the BL register. Then we store our answer in the AX register. We see the value 32 hex in the AX register converted to decimal. This is 50. The input values were stored in 8-bit registers AL and BL, but the result is stored in the 16-bit AX register. In this example, we will use slightly larger values, but still storing them in the 8-bit AL and BL registers, then performing the multiplication to show why it is necessary to store the answer in AX, a 16-bit register. Finally, we will see a multiplication operation using 16-bit registers AX and BX for the inputs. In this example, the value 250 is stored in the 16-bit AX register. Remember, the register is displayed in hex, not decimal. The second value, 1000, is stored in the 16-bit BX register. Then we execute the multiply BX instruction, multiplying 250 by 1000. Just like in the previous examples, more than 16 bits may be required to store the result, so we store the lower 16 bits in the AX register, but we will also use the DX register to hold the upper 16 bits. 250 times 1000, which is 3D090 hex, composed of the 0003 hex in DX and the D090 hex in AX. It is best to avoid using a combination of 8-bit and 16-bit registers, as can be seen here with AL being used with BX. In this case, the BX register will force the multiplication to be performed on the AX register, and there's no way to know the contents of AH since we haven't explicitly set those bits. Likewise, if we store a 16-bit value in AX, but perform the multiplication using BL, only the 8 bits of AL will be used for the multiplication, ignoring the upper 8 bits of AX. Now we will quickly look at two different simple division problems. First, we have 10 divided by 2, so we move 10 into AL and 2 into BL. Then we execute the division instruction using BL. The result is stored in AX, just like in multiplication. The result uses the entire 16-bit AX register, even though AL and BL are 8-bit registers. And we see our answer of 10 divided by 2 equals 5. Now for our final example, we will execute the same problem, but we'll substitute 11 for 10 in the AL register. This time we see a totally unexpected answer in the AX register. Instead of seeing 5, we see 0105 hex. In this case, we are really seeing the AX register split into the AH and AL halves, with AL containing the whole number quotient and AH containing the whole number remainder. Here we have 5 with a remainder of 1, and the previous division problem was actually 5 with a remainder of 0. Now that we understand basic data transfer using the move instruction and basic arithmetic instructions, add, subtract, multiply, and divide, let's write our first program to convert a temperature from Fahrenheit to centigrade. Before we start Visual Studio, let's look at the equation we will be using for our program. The equation should be somewhat familiar, but we intuitively know how to solve the problem. When we are thinking about computer programming at a low level, such as assembly, we have to intentionally pay attention to the order in which the program will execute. First, we'll set a variable in the data segment called f and we'll store the value 50. Second, we'll subtract 32 from the value we stored in f. This is accomplished by moving f into AL, then moving 32 into BL, and finally subtracting BL from AL, storing the result in AL. Next, we will multiply the result from step 2 by 5 by moving 5 into BL, then executing the multiply instruction using BL. Finally, we will divide the result from step 3 by 9 by moving 9 into BL and then executing the divide instruction using BL. The result will be stored in the AX register at this point. Remember, AL, the lower 8 bits, are the quotient, and AH are the remainder. Now let's write the program and run it in Visual Studio. Start Visual Studio, click Create a New Project, select your x86 template using the search bar if necessary, and click Next. Give your program a descriptive name, such as Lab 1 Temperature F to C, then click Create. When the Visual Studio Develop environment opens, make sure your main template is open in the large window. The first thing we will do is add a line between line 2 and 3 to define our Fahrenheit temperature. We will use 50 degrees. F tab dB tab 50. Now highlight line 13 where it says add your program code here and delete the text. We will now type our program, including explanatory comments for each line. Remember, comments are important to explain tricky parts of code, or as a future reminder of what you are trying to accomplish with the code. Move AL, F. Move Fahrenheit temperature to AL register. Move BL, 32. Move 32 into BL register. Sub AL, BL. Subtract BL 32 from AL Fahrenheit temperature. Move BL, 5. Move 5 into the BL register. Multiply BL. Multiply AL, which is F minus 32, by BL, 5. Move BL, 9. Move 9 into the BL register. Divide BL. Divide AL, which is now the Fahrenheit temperature minus 32 times 5, by BL, 9. Set your breakpoint on line 14 by clicking in the gray bar to the left of line 14. Once all lines are entered, remember to click Save All to make sure your program is saved. Now click Build, Build Solution, and confirm in the output window that it succeeded. Now click Debug, Start Debugging. If your registers are not showing, remember to click Debug, Windows, then Registers. I have the registers shown across the top of my screen. Notice the breakpoint has a yellow arrow. This is the line before which the program has paused. Toward the top of the header, you will see a down arrow with a dot. This is called Step Into. We will use this to step through our program one line at a time, looking at the registers as we go. Click Step Into and observe EAX now shows 32 in the AL part of the register. 32 hex is 50 decimal, our value for F. Each affected register will turn red, which will help us see the changes. Click Step Into. This time looking at EBX, we have moved 32 decimal into BL, showing 20 hex. Now clicking Step Into performs the subtraction of 32 from 50, and AL shows 12 hex or 18 in decimal. Click Step Into to move 5 into BL. Step Into again will now execute the multiplication instruction showing 005A in hex or 90 in the AX register. Finally, clicking Step Into 2 more times will first move 9 into BL, then divide the value in AX by 9. The result of our conversion is now shown in the AX register, 10 with the remainder of 0. Click the Stop button. Feel free to change the value of F on line 3 to other numbers. Rebuild the project and run debug again. If you don't need to see each step as you rerun the program, feel free to move the breakpoint to line 25, the return instruction. And one shortcut. Once you change the value of F, you can quickly save, build, and debug your program by simply pressing the F5 key. Just make sure to click Stop after your program runs before making changes. This concludes this video.